So, good evening and welcome everyone to the 11th Keeling lecture. I'm Ralph Keeling. I'm the son of Keeling. That's hopefully a good thing. Anyway, it's such a great pleasure to be back here in this setting. I think all of us have not particularly enjoyed the last 2 years hiatus of interaction. And there was, of course, a couple-year hiatus in the Keeling lecture, but it's so great to get this back on track and going again. And it's so great to see a wonderful crowd here tonight. So a little bit about the background of this lecture. So the lecture series is in honor of my father, Charles D. Keeling, who did early work on climate change, and he helped move the science of climate change from theory to fact, and he did that through careful observations documenting what was really happening. And the curve that bears his name, the Keeling Curve, remains kind of this icon of reality. Like, if you think this isn't a problem, look at this. And so this lecture series is to just extend that legacy into the science of climate change and the policy of climate change, wherever that takes us. And of course, right now, climate change isn't just a problem for the future. It's here. It's here and now. And here in the West, the big issues that I think we're all aware of are heat waves, they're drought, they're fire. If you haven't been noticing that we're getting more fires, or at least more big fires, you haven't been paying attention. And it's a serious issue, what happens going forward. And I'm very pleased that we have a speaker that will address some of these issues that are really at the forefront of the science and public thinking. Park Williams comes to us from UCLA. Like me, he's a California native who managed to make his way back to the West. He did his undergraduate work at UC Irvine, right up the street. He then went on and did graduate studies at UC Santa Barbara, spent a little time back east, as I said, and now he's a colleague in the geography department at UCLA. His work addresses questions like, why are there more big fires? Is this drought that we're going through now? Why is it? How big a drought is it? What are its origins? So it's really at the forefront of these major questions. So I'm really eager to hear his stories. He's got a lot of stories, but I'm so great to have a chance to bring him in our midst and welcome him to San Diego and welcome him to California again, because he's actually only recently moved back, and hear what he has to say. So thank you so much.
Well, I give a lot of talks, but I haven't been as nervous to give a talk as I am now for a while, because they're just such huge shoes to fill. I, of course, never got to meet Charles Keeling, but I've been familiar with the Keeling Curve since I was an undergrad. It no doubt influenced the trajectory of my life and helped me identify what are the important things to really understand about our planet. And then some of my heroes had given this talk before, and so when I received the invitation, I was just totally blown away. So thanks all for coming, and thank you for the invitation. Probably for as long as humans have existed, they have looked at the landscape and wondered why things look the way they look, and every once in a while they probably saw evidence that the landscape that they are on once upon a time was subject to a totally different climate than the one that they're currently looking at. We don't, as far as I know, have verbal stories that actually give us a memory of the last ice age, which ended somewhere between 18 and 15,000 years ago. But we see evidence of the last ice age all over the place. And when we finally do have written accounts by people telling stories of what they think climate was like on the landscapes they were interested in, about 2,000 years ago, we have written records of speculation that erratic boulders like this must have been deposited by glaciers. And it's just amazing to think that a landscape that has no glaciers could have once upon a time been covered by a river of ice carrying gigantic boulders and dropping them in place. In the 1800s, our understanding of Earth's climate system was advanced enough that theories were actually being formalized about how these past ice ages could have formed. It was understood that Earth's tilt changes and that Earth's distance from the sun changes, and maybe that played a role in driving the ice ages. And it was also being understood that greenhouse gases exist. In the 1850s and 60s, greenhouse gases were actually observed for the first time in a laboratory. And by the end of the 1800s, it was being speculated that burning of fossil fuels, coal, was actually causing carbon dioxide, a known greenhouse gas, to accumulate in the atmosphere, and that might someday cause the Earth's climate to actually warm. And if it went on for a long time, hundreds of years or thousands of years, it could eventually, potentially, make Earth's habitability noticeably change. But in the late 1800s, early 1900s, we didn't have records of CO2. So this was just speculation. We knew we were burning a lot of coal, and we knew that CO2 probably doesn't come out of the atmosphere that quickly. So it was probably accumulated in the atmosphere. We also didn't have great records of global temperatures. But by the late 1930s, we did have records of global temperatures, not from tons of places, but from enough places that the data could be stitched together. Of course, we didn't have the internet. We didn't have a really good mail system, and so compiling records of temperature from all over the planet took huge amounts of work. But by 1938, somebody had done it, and they showed, indeed, temperatures are rising. Over that 50-year period, temperatures risen by a couple of tenths of a degree, and it was actually noticeable in the temperature records. But we still didn't know what was going on with carbon dioxide. There had been efforts to measure carbon dioxide in the atmosphere, but prior to the mid-1950s, these measurements were all over the place. There were instrumental problems and problems with where people were measuring it. People were measuring carbon dioxide generally close to where they worked, and where they worked was generally in cities, and so they were measuring the carbon dioxide not necessarily of the free, open atmosphere, but potentially just of a local source. And so as you can see here, this record starting in 1800, going through the mid-1950s, our observations of atmospheric CO2 are all over the place. And so it was impossible to assess at that point whether or not CO2 is actually increasing in the atmosphere, and if so, at what rate. As most people in this room know, this is really what Charles Keeling became famous for, is he developed the technology to be able to make precise measurements of atmospheric CO2. And we're looking here at the iconic Keeling Curve that Ralph just illustrated. And when this record from the top of a volcano in Hawaii was initiated in 1958, we were somewhere around 313, 315 parts per million. That means for every million parts of the atmosphere, about 315 of those parts was made up of CO2 molecules. And now we just set a new record, which we get to set every single spring, and the record was 421, or the record currently is 421 parts per million. And so what we're seeing here is a record of the atmosphere's chemistry changing profoundly. And this was important because it nailed down the other part of this narrative that was developing about fossil fuel burning and climate change. We knew as early as the late 1930s that warming was occurring, and then we knew as early as the early to mid 1960s that indeed carbon dioxide is accumulated in the atmosphere, and this is what it's been doing since then. Now, Charles Keeling wasn't measuring CO2 precisely before the 1950s, but it turns out that ice cores were. Ice cores on Greenland and Antarctica are made of tubes of ice that we can dig out of the ice caps, and because snow is laid down in sequential order, it buries with it old ancient atmosphere. And so we can dig into the depths of the ice caps and actually measure what the chemistry of the atmosphere was like before we were measuring it precisely. This just goes back to the year 1700. And we can see from ice cores on Antarctica that prior to the Industrial Revolution, the CO2 levels were in the range of 270 or 280 parts per million. And so this gives us a little more context to see this chemistry experiment that we're running with the atmosphere really is serious. But we can actually go back further than that. This record now goes back 800,000 years. And here we can see these glacial cycles that scientists have been trying to understand for hundreds of years. We can see that during the warm periods, CO2 was higher. During cold periods, CO2 was lower. And the most important part is that now we are just absolutely totally off the charts of anything that the Earth has experienced in the last million years. And very likely, CO2 hasn't been this high in about 3.3 million years. Meaning CO2 hasn't been this high any time during the time that our species has been on this planet. And so it's no surprise then that the warming that was observed by the late 1930s has continued. And now, after 150, 200 years of really rapid CO2 accumulation in the atmosphere, the globe is on average warmed by about 2.25 degrees Fahrenheit. Now that's a global average. Most of the globe is covered in ocean. It's hard to change the temperature of ocean. Land changes temperature more, and so land temperatures have actually warmed quite a bit more than this, probably closer to 3 or 3.5 degrees Fahrenheit. So this is what Charles Keeling is most known for. But if you go back and see how it all got started, it gets started the way that profound discoveries often get started, and that's by somebody having fun, somebody exploring their innate interests. If we go back to some of these initial papers where Charles Keeling was first showing data from his initial precise measurements of CO2, he doesn't actually have a paper, as far as I know, that demonstrates or describes the method of measuring CO2 for the first time precisely. Instead, he just starts showing really cool results. In his late 20s, I believe it was his late 20s, he starts driving all over the western United States, going to remote places that are thought to be pristine, so not measuring the atmosphere in cities, but measuring the atmosphere in mountain areas. One of the first trips was to Big Sur. He has all kinds of measurements from the Pacific Northwest as well. And the first really cool thing that he discovered was this daily cycle in atmospheric CO2. And the only way that you could measure a daily cycle in CO2 is if you're measuring CO2 very precisely. And so this must have been a lot of fun for him, creating new data that just has totally unprecedented precision, being able to understand something about the Earth system that has never been seen before. The measurements continued, and because these measurements were so special, he was able to establish these measurements, long-term monitoring systems to make these measurements on Mauna Loa, Hawaii, as well as the South Pole. And here in the Northern Hemisphere, after a couple years of measuring, they noticed something really interesting. Not only does CO2 have a daily cycle, but it also has an annual cycle. And they figured out pretty quickly that this is the Earth breathing. This is the biosphere breathing. During summer, plants grow, and when plants grow, they take CO2 out of the atmosphere, and so CO2 concentrations go down. And then in the winter, they stop growing, respiration starts exceeding photosynthesis, and CO2 breathes back into the atmosphere. And so they saw this annual cycle, and they saw maybe a hint of an increase in CO2 here, but it was hard to see because of the annual cycle. But you go to Antarctica, the South Pole, and the South Pole is atmospherically pretty isolated from the nearest big forests, and they just see the beginnings of an increase. And this initial paper that's showing these initial measurements in the abstract notes this increase. And they say this increase needs more, we need more research to understand the rate of change or the cause of this increase. Something else that's really neat in these initial, or in this data set that Charles Keeling is responsible for, besides just the long-term increase in CO2, is what's going on beneath the increase. So if you take away that seasonal cycle, and if you remove the long-term increase, it turns out that global atmospheric CO2 is oscillating in other ways that are independent of those other processes. And it turns out that that is, again, the biosphere breathing. But it's driven by ocean currents. As El Nino sloshes back and forth in the Pacific Ocean, the atmospheric circulation changes and actually causes the distribution of water across the continents to change. Locations of giant fires change, depending on whether it's an El Nino year or a La Nina year. And so either the atmosphere is giving up a bunch of CO2, or the biosphere is giving up CO2 to the atmosphere, or pulling CO2 out of the atmosphere connected to ocean currents. This is not a discovery that Charles Keeling is most famous for, but he was part of this team that discovered this, and I think it's just so important and really cool and very influential to me. And so there are a couple of really big key lessons that we can take from some of this work that I just overviewed. One is that we have clearly now embarked on an atmospheric chemistry experiment that is putting us really in uncharted territory. CO2 has been as high as it is now in deeper times in Earth's past, but never a time when humans are also on the planet. And so we now know today that we are in uncharted territory, and we need to really work as hard as we can to understand why this is. And one of the keys to understanding our planet is making precise and consistent long-term measurements, and Charles Keeling demonstrated that. The other is that when you change the climate of the Earth, you change the distribution of water across the continents. And when the distribution of water across the continents change, then the distribution of life across the continents has to change as well. Water is one of the things that's most important to life. And we actually do not need to look back far in Earth's climate history to see really, really clear examples of this. Most people don't know that just 6,000 years ago, one of the driest parts of the planet, the Sahara Desert, was actually green. It wasn't a sand-covered desert. There was vegetation. There were swimming holes that people were at, painting what life looked like on these in this savanna setting just 6,000 years ago. Pictures of rhinoceros and other animals that require large amounts of vegetation to survive. Large amounts of vegetation, of course, requires water. The thing that allowed this to happen is just a slight difference in Earth's tilt that caused summer times in the northern hemisphere to get more sunlight than they do today. And that changed the latitude that the tropical monsoons occur across northern Africa. At the same time that northern Africa was green and abundant with life, the western US actually appears to have been much drier than it is today. This picture is of a Native American grinding stone site that is currently about 20 meters deep, or about 60 feet deep, in Lake Tahoe. It's believed that this site was a shoreline site about 6,000 years ago. The only way that this site could have been a shoreline site 6,000 years ago is if climate was 6,000 years ago was much drier in the western United States than it is today, for a long time. The western United States is undergoing a climate trend right now toward drying. In the news every day is the news about Lake Mead hitting a record low, Lake Powell hitting a record low. These are the largest lakes in the United States, and they're both hitting record lows, not just because of one dry year, but because over the last 23 years, 19 of them have been dry. If you go back to, if you look at Treering records, there's one other 23-year period where 19 of the years were dry in the last 1,200 years. So this is a serious drought. Because drying has been outweighing wet conditions so strongly across the West, humans have been coping, and many of you probably think would say, well, this drought just hasn't felt that bad. Well, we've been drawing really heavily on a backstop, groundwater. We've been pulling groundwater out of California's Central Valley so hard that the elevation of the ground in the Central Valley has actually shrunk by several feet or more in some places. So we're squeezing out this sponge, and a lot of the Central Valley, this water was deposited there when the glaciers melted about 15,000 years ago. So it's not quick to be replaced, and especially once the ground gets scrunched down as we dry it out. We've seen giant outbreaks of bark beetles as our forests have increased in their experience of drought stress. We have seen a giant increase in wildfire activity, especially in forests, as Ralph mentioned a minute ago. And we've definitely seen some of the driest conditions that have occurred in the last century. This is a map of a data set that I update every month, where every month I calculate the moisture balance of the soil. So I look at how much precipitation fell out of the sky. And I also look at variables important for evaporation, temperature, sunlight, wind speed, and humidity, and I calculate the moisture balance of the soil. What we're looking at here is a map of how soil moisture dryness last year ranked compared to all other summers since 1901. And so the darkest brown areas are areas where 2021 was the driest summer on record, And what you can see is that not everywhere was driest on record in 2021, but the vast majority of the western United States was dry. We're hearing about drought a lot in the news right now, and the reason is because 2022 is looking a lot like 2021. We haven't experienced summer yet, so here we're just looking at, oh, sorry, I deleted the slide. So the data, of course, just now come through April, but if we make some assumptions about what climate might be like for the next few months, where we just hope that we get something that looks like the long-term average, then we see that this drought in 2020, or the drought conditions in 2022 are once again going to be really strong. This has big implications for our upcoming fire season because, as we all know now, here at the beginning of May, our rainy season is probably over. And so whatever water we have in the soil now, that's kind of what we're stuck with for the next several years. So for the next few minutes, I'm going to talk about the western United States and northern Mexico, and I'm going to talk about this box here, and I'm going to call this box the Southwest North American region. This is because North America includes a lot more than the western U.S., and so this is the southwest part of North America, although it includes parts of northwest continental United States. And if we just take the average soil moisture in this red box and make a record of that, this is what it looks like for the last 122 years. And so you can see a lot of ups, a lot of downs, but then in the last 23 years, a lot more down than up. And this is what I was talking about. There have been 4 or 5 wet years in the last 23 years, but something like 19 dry years. And so it's really clear that the last 23 years are the driest 23 years in our observational record since 1901. But we also know that it can get dry and it can get wet on its own in this region, so before just automatically evoking, oh, this is because of human-caused climate change, we should be really careful. Like I just showed you, that we have evidence across the landscape that climate can go through these monumental swings without the assistance of human-caused climate change. Here's another underwater photo from the Sierra Nevada mountains, again from about 6,000 years ago. This is a lodgepole, this is about from 1,000 years ago. There's a lodgepole pine that is still rooted to the bottom of a lake in Yosemite. This means that 1,000 years ago, this lake in Yosemite must have been lower for something like a century, long enough for this tree to grow to this size. We see riverbeds that are consistently too wet these days to sustain forests, and we see these ancient stumps, again dating to about 1,000 years ago. We see Native American ruins where we can use Treering records to date when these societies were really booming, and then when they busted, when they became depopulated. And in the 1200s, this is when Mesa Verde was depopulated. This coincided with a naturally occurring, very long-lasting severe drought. And so we should be careful before just assuming that our drought is fully because of human-caused climate change. Climate can cause the water distribution in the West to change on its own. But let's dig into this a little bit. We can study the past of drought in Western North America actually better than we can in most parts of the world because we have a giant amount of tree ring data. Here's a cross-section of a Douglas fir tree from Arizona. You can see annual growth rings. You can see sometimes when the growth rings are really wide. You can see other times when the growth rings are really skinny. The skinny rings coincide, of course, with years when growth was really slow. The wide rings coincide with years when growth was really rapid. And so in a place where trees are really living and dying by the amount of water available, we can interpret these ring width variations to be variations in water availability. What we're looking at here is actually a megadrought. The term megadrought came up in the 1900s, but it really represents droughts that we know about from the tree ring record that are more severe and longer lasting than anything that modern society of the 1800s and 1900s really had to contend with. This was the last gasp of the megadrought era of the medieval period. This was in the late 1500s, so just after the medieval period. We have tree ring records from all over the West, and long ones. Now, I have collected some tree ring records, but there's no way that I've collected this many tree ring records. We have tree ring records from tens of thousands of trees, And for over a century, tree ring scientists have been collecting tree ring records. We don't need to chop down trees to get our data. We can actually stick a metal tube called an increment borer into a tree by just screwing it in and pulling out a dowel of wood, kind of like a biopsy, and we can observe the cross-section of tree rings that way without actually hurting the tree. Tree ring scientists have been collecting data in the western US for a century and making the data available. They've been sharing with their friends, and we're able today to be able to use tree ring records that have been collected by hundreds of tree ring scientists over the years. I've taken this tree ring data set and all over the West have made reconstructions of what soil moisture was back in time. This can be illustrated here. I'm not showing you far back in time yet, but I'm showing you in red that same soil moisture record that I showed you earlier, which is the average of soil moisture across this Southwest North American study region. And then black is the estimate of soil moisture during the period of overlap from 1901 through 2000 based on tree ring records. So these tree ring records haven't been told what the climate data are that I'm using to make these soil moisture records. The tree ring records are telling us how much water they had to deal with, and you can see the two lie on top of each other really, really well. Because the trees can tell us so precisely how much water was in the soil in any given year, and because the trees have been sitting on the landscape far longer than our weather stations, we can reconstruct soil moisture back in time going at least back to the year 800 AD, pretty precisely, in Western North America. And so the black record here is our tree ring record of soil moisture. The red is the observations I was just showing you, and you notice that it's a lot smoother than the record I was just showing you. That's because I've done an averaging window across the whole thing, taking away the year-to-year noise so we can see what's going on from decade to decade. And specifically, this averaging window is 23 years long. That's because in the Western United States, it started getting really dry in the year 2000, and it's now been 23 years since we've really seen serious wet conditions in the West. So our drought is currently 23 years long. I'd like to see how the magnitude of this 23-year drought compares to the magnitude of other drought conditions in all the other 23-year periods in the last 1,200 years. And what we can see is that now, after 23 years, we have experienced a larger average drought severity than at any other time, even during these infamous megadroughts. So what causes a drought? Well, the first cause, the primary cause of a drought is just lack of precipitation, obviously. So let's look at our precipitation record. The black record is the average annual precipitation across southwestern North America, and you can see there are a lot of wet years, a lot of dry years, and during our 2000s drought period, the majority of the years have been dry, but not all. You can also see some interesting things, like there's not a long-term trend. And so when we hear that human-caused climate change causes drying, this suggests to us that it's not causing drying from a precipitation perspective. We actually haven't seen a reduction in precipitation over the last century. And we can even ask climate models. What do climate models say should occur or should happen to precipitation because of greenhouse gases in the atmosphere in the western United States? And the climate models are actually all over the place, but when you average them all together, they say no real trend. So how would climate change be affecting drought severity in the West? Well, the answer is through temperature. And specifically, it's through this variable that not many people have heard of, but it's really important. It's called the vapor pressure deficit. So when temperatures are warm, as anybody knows who keeps houseplants, things dry out faster. And the vapor pressure deficit is the combination of heat, which allows the atmosphere to pull more water, to hold more water, and the amount of water vapor in the air. So it's a combination of heat and humidity. And what we can see is because of warming in the western US, the black record of vapor pressure deficit is going up. We've seen a significant increase in the vapor pressure deficit, meaning the atmosphere has become thirstier, it's become spongier. We can ask climate models, what do climate models say should happen to the vapor pressure deficit because of the accumulation of greenhouse gases in the atmosphere? And they agree dead on with the magnitude of the trend in the vapor pressure deficit that we've seen in the real world. So now we can go back to our soil moisture calculations and we can say, okay, well, what's the contribution of this trend to the record of soil moisture that I was showing you earlier? And that's what I'm showing you now. The black record is our observation-based record of soil moisture, the one I was showing you earlier. Here's our drought period of the last 23 years. And then the teal is the contribution from human-caused warming vapor pressure deficit trends. And what you can see is that clearly the trend toward a warmer atmosphere hasn't been the absolute cause of the drought conditions. It doesn't account for the full magnitude of the severity of the dryness, but it's been encouraging the dryness. We've still had wet years during this drought, but it's harder for a wet year to be as wet as it would have in the 1900s because the baseline is changing. So what we would call an average year now is drier than what we would have called an average year as recently as the 1970s or 80s. And this has caused what would be a naturally occurring drought that would be quite a serious drought even without climate change. Human-caused warming has caused this drought very likely to be, or human-caused warming is responsible for this drought being able to beat out these infamous megadroughts of the medieval period in the late 1500s. And so here I'm just showing you our observed drought, and the red line going along the bottom is the magnitude, the severity of the last 23 years. And then in blue is a recalculation of how bad the drought would have been without human-caused warming trends. And what you can see is it still would have been a bad drought. It still would have pretty easily been the worst drought in 300 or 400 years, but it wouldn't be as bad as these big megadroughts. And very likely, if we look at these megadroughts, you can get an idea of what a normal lifespan is of a megadrought. The megadroughts lasted anywhere between 23 years and 30 years. And so without climate change, we could be expecting our bad luck to reverse and for wet conditions to come back in a year. Because the average year is getting drier and drier, we can expect that this megadrought is going to probably last longer. It will eventually end. You can see a lot of ups and downs. There's still a lot of room for good luck to come and give us a good decade. But it's going to be harder and harder in the future for good luck to bail us out of a drought. And it'll be easier and easier for a little bit of bad luck to throw us right back into a drought. One of the most tangible ways that droughts affect us is through forest fires. And in California, we are especially familiar with forest fires because 2020 and 2021, as I'll show in a few minutes, have really been spectacularly bad forest fire years. This is just showing you maps of the areas of California that burned in just in the last 2 years. Now, I was saying earlier that some of my heroes have given this talk before. In 2010, the very first Charles Keeling Memorial Lecture was by Steve Running, one of my heroes. And I was watching that talk, doing my homework for this talk. And in that talk, he started talking about fire. And he said in 2010, fire represents the greatest potential for human vulnerability in the West. That's saying something, because there are a lot of things we're vulnerable to. We're vulnerable to disease, we're vulnerable to nuclear war, we're vulnerable to lack of groundwater. But he was seeing in 2010 that fire was going to be a really serious issue for us. And part of the reason he said that is because in 2010 it was already pretty clear that there was a fire trend, but that trend has become a lot more clear in the last 11 years. Here I'm showing you a record of the amount of area that has burned in wildfires in the western United States since 1984. The reason I start in 1984 is because that's when our satellite records of burned areas start being really precise. But this trend has been going further back than 1984. This just wasn't just a conveniently picked year. This trend goes back at least to the 1940s or 50s. And so most people see this plot, and Steve Running, the way he would have described this plot, at least in the context of that quote, is this is bad news. Fire, we humans don't like fire because it's too hot. It burns our stuff, and we don't like the smoke. But fire is, of course, a natural process as well. Fire has been on the continents for as long as plants have been on the continents. If you walk around any old-growth forests in California, you'll see evidence of ancient fires in abundance. You see fire scars left on trees in the coast redwoods and giant sequoias. If you look at the cross-section of tree rings from ancient trees, you see evidence of fires in many of our western U.S. forests occurring repeatedly. So fire isn't inherently a bad thing, but we are really having a tough time with it. We are increasingly in harm's way of fire, either directly or because of smoke. Even people who choose to not live in areas that are really flammable are increasingly being exposed to the enormous health consequences of big fires through smoke pollution. Smoke pollution may end up being what is someday seen as the biggest integrator of climate change as a human hazard in the western United States. If climate change is responsible or partly responsible for causing this big increase in fires, then many of us may be in harm's way, not just those of us who live where the flames actually are. Fires enhance runoff, and they can promote mudslides, so they can promote flooding hazards. They also cause hazards regarding water quality. And the fires that we're seeing today are oftentimes not even the type of fire that forest ecosystems really agree with. In the southwestern U.S., if you drive around the mountains of the southwest, you see ponderosa pine trees. Ponderosa pines actually are not very good at getting their seeds very far from the parents. That means that if you open up a giant canopy of ponderosa pine forest like this, it could take hundreds, maybe even thousands of years for seeds to be able to migrate back into the center of this patch and fully recolonize this burned area. But if we look at the tree ring records of fire, we can see that prior to the 1900s, ponderosa pine forests in the southwest were burning every 5 to 15 years. So how is that? How is a tree that's not very good at surviving giant fires also a tree that can have fires burning every 5 to 15 years? Well, before we started interfering with forest ecosystems by putting out fires, fires were keeping the density of ponderosa pine forests lower than they are today. And so very likely the fires that were burning every 5 to 15 years were burning at a much lower intensity than fires that are intense enough to take out many square miles of ponderosa pines all at once. So it's kind of a mixed bag whether or not an increase in fire activity is a good thing or a bad thing, but it's pretty clear that from the human perspective, it's a bad thing. The red record is the record I was just showing you, showing this trend toward more fire, and the green record is now the amount of money that the US federal government spends fighting fire every year. And so this increase, sometimes you'll hear, well, the increase in fire is because we're letting fires burn more. That's not true. We're fighting fire. Okay, occasionally we might let a fire burn more if we see it going into an area that we really want to burn, but we still try as hard as we can to put out almost every single fire, and that's really expressed pretty clearly in this data set. And yet, fires, despite our best efforts, are growing. And so we, for a century, had control of the fire regime in the western US. We were very good at putting out fires, and just in the last couple of decades, despite our best efforts, fires have been increasingly escaping us. Why is this occurring? Well, the first thing we should do if we want to know why it's occurring is we should know where it's occurring. And I can kind of simply break this out for you by just showing you that fire record, but split into two. On the left, I'm showing you the area burned every year in forests of the western US. And in brown, I'm showing you the area burned every year in areas that are not forests, so grassland, shrubland, chaparral. You can see that the area burned is increasing in both areas. And if we weren't experiencing this giant increase in forest fire, then this would be more interesting, that we've seen more than a doubling in the annual area burned in non-forests. But the reason why fires are growing so dramatically is really because forest fires are growing so dramatically. These days, the average year has something like 13 times as much area burned in forests than would be expected in the average year of the 1970s or 1980s. Why is this? Well, we can do all kinds of statistical analyses comparing this forest fire record to different climate variables. I'll save you all of the plots, and I'll show you the key one. A few minutes ago, I introduced to you the vapor pressure deficit. This is the aridity of the atmosphere, the sponginess of the atmosphere. It's dictated by heat and humidity. Here, every single dot represents one of the years between 1984 and 2021. On the horizontal axis, we're looking at the vapor pressure deficit of each year. On the vertical axis, we're looking at the number of millions of forest acres that burned. And the fact that we see all these dots lined up nicely on this line means that there's a really strong correlation. The hotter and drier the atmosphere, the more forest fire there is. This relationship is, to me, surprisingly strong, given the amount of chaos involved in individual fire. An individual fire oftentimes is set by a person at a random time. An individual fire requires intense winds that are not necessarily related to global warming in the vapor pressure deficit. People then start trying to put out every individual fire. And yet at the end of the year, the amount of forest area that burned is pretty predictable as long as you know how hot and dry the atmosphere was. Not only does the heat and the dryness of the atmosphere serve as a really good predictor of the amount of forest fire that burned in any given year, but you can compare the colors of these dots to see that it is also the driver of the huge increase in fire from the 1900s to the 2000s. The blue dots represent years in the 1900s. The red dots represent years in the 2000s. And the red dots are all over here on the warm, dry side of this plot. The blue dots are over here on the cool, wet side of the plot. And so as the Western United States climate has dried over the last several decades due to the combination of bad luck, lack of precipitation, like I showed earlier, and human-caused warming, then fire has kind of just slid up to the top right corner of this plot the way that you'd expect. But there's a key thing about this plot, and this is as deep into statistics that we'll get in this talk, but this vertical axis here, if you look carefully, these numbers aren't going up in a linear fashion. Instead, they're increasing exponentially. And the reason I do this is to show that fire is so predictable based on this single variable. But if I take this off of its logarithmic plot, then this is the actual relationship between burned area and the vapor pressure deficit. And so if you've been wondering why fire went from being something that we noticed every once in a while, large fires being something we noticed every once in a while a few decades ago, to really making the news every single summer, and records being broken for biggest fire nearly every summer, and career-long firefighters saying that they're seeing fire activity that they have never seen before in their entire career. It's because this is exponential. What this means is that for every little bit of drying and warming that we see in the West, the amount of extra forest fire you get is bigger than the amount of forest fire you got from the same amount of drying before that. This has huge implications for the future because as long as I'm correct that human-caused warming is promoting a drying trend in the Western United States, then you can envision that we might be inching our way even further to the right on this plot. And that means that these record-breaking, really extreme fire years might, in another decade or so, actually be the norm rather than the exception. But many of you are probably thinking, well, there's a whole lot more that affects fire than just climate. And that's absolutely correct. There are a lot of things that are really important to fire. And so I was just talking about the dryness component. But of course, you can dry out a desert all you want. If there's not enough to burn, then you're not going to get fire. And so fuels must be important. And then you can dry out a forest as much as you want, but if you don't get a spark, you're not going to get fire. And so ignitions must be really important as well. And so if you just look at these extremely different landscapes, they're only 100 or so miles apart from each other, you can see that in this dense forest in the southern Sierra Nevada, probably all you need to do in this forest to promote fire is dry it out and add a spark. There's plenty to burn. Whereas over here in this desert scene, it's already dry enough where all this vegetation could burn at any given time, but there's not enough vegetation to carry big fires in most years. And so the way to get a fire over here is actually to have a really wet year, grow a whole bunch of new grass, and then have a dry year to dry it out. And so if we go back to this analysis I was showing you a little bit ago, where I showed in forests that the amount of forest fire that we get is so sensitive to how warm and dry the atmosphere is. And then if I repeat that same analysis for the non-forested areas, you see the same rule applies. The warmer and drier the atmosphere is, the more fire you get. But there's a lot more variability. There's a much less strong response because outside of forested areas, it requires so much more. And you are all familiar with this if you live in San Diego outside of forests, and you see that in order to have a big fire in San Diego, oftentimes you need a big Santa Ana wind event. And a big Santa Ana wind event is only going to cause a big fire if you haven't had the onset of the winter rains yet. So there's a lot that a fire requires outside of forests, but things are pretty simple inside of forests. Well, we hear all the time, though, about how forest mismanagement might be part of the problem with this increase in forest fire. How could that square with what I just showed, where I just showed that the warming trend is what caused the big increase in forest fire sizes? Well, it turns out that we can actually have both things be true. And we can illustrate that nicely just by looking at this, this repeat photograph from Yosemite Valley. About 110 years apart, you see that 110 years ago, or 120 years ago now, Yosemite Valley there's a lot more open area. The forest is much less dense, very likely because fire had been going through here all the time. Native Americans were lighting fires in this valley probably for thousands of years. Then Western or European civilization shows up in the West and starts stamping out fire, and we did so successfully for 100 years, and so we have a totally different forest ecosystem. If you dry out this forest ecosystem, you're very likely to get a much bigger, more energetic fire than if you dry out this forest ecosystem. And so the drying and the heating of the atmosphere is what has driven the increase in forest fire activity that we've seen, but forest fire activity wouldn't be allowed to be as sensitive to the drying if it wasn't for some forests or many forests being artificially stocked with trees because we've been putting fires out for a century now. But that story isn't the same everywhere. In the Southwest earlier, I was telling you that without fire suppression, we'd have fires going every 5 to 15 years. And so if we've fought fires successfully for a century in the Southwest, that means we've successfully fought on average 10 fires. And so those forests look a lot different than they would without us. Whereas in the Pacific Northwest, a lot of these forests are so wet that we probably haven't had an opportunity to put out many fires in a lot of Pacific Northwest forests. And so this narrative that we have caused the fire problem by putting all the fires out for a century is much more applicable in the Southwest US than it is in wetter areas like the Pacific Northwest. We also hear the hypothesis that human ignitions must be part of the problem. Across the western United States, just in the 20 years from 1990 to 2010, human population increased by 36%. That's a lot of extra people. In flammable areas, these areas called the so-called wildland-urban interface, these are neighborhoods that are right up against dense flammable vegetation, the human population has actually increased during that time by over 50%. Humans are, of course, the source of many fires. We don't set fires on purpose very often. Generally, it's occurring by accident or through our equipment. And so you could easily make the case that the increase in population is leading to increased cases of accidental fires, and that must be playing a role as well. Well, let's look. Here's a record of the number of large forest fires in the western United States since 1984. And we see that there is indeed an increase, that the number of fires on average, in an average year, has increased by about 60%. But remember I showed you earlier the area burned has increased by over 1,300%. If you go outside of forests, and this is actually where most of the people are obviously living, you actually see a reduction in the frequency of fires since the mid-1980s. This is because not only are people good at accidentally starting fires, but they're also very good at putting out fires. And we've become more careful over time. There's less cigarette smoking now than there was in the mid-1980s. There are more roads chopping up grassland into segmented chunks that can't carry fire as easily. And so the increase in human population is very clearly not the driver of the huge increase in forest fire activity. Now, obviously, many individual fires were caused by people, and you can make the case that if people weren't there, then that fire wouldn't have occurred. But the big increase that we've seen from the 1980s to present is not due to the increase in population during that time. That's kind of hammered home even more. This is a shorter fire data set. This one starts in just 1992, but we can actually, with this data set, split fires out into fires caused by lightning versus fires caused by people. And you can see that the fires are getting larger for both types, but clearly it's the lightning-induced fires that are actually driving the big increase in forest fire. Now you can look at a lightning data set and you actually see that lightning has not been becoming more frequent. It's just the potency of lightning to be able to drive big fires because forests are drier than they were 30 or 40 years ago. So what's going to happen in the future? I showed earlier that the future is really concerning because the response of forest fire to atmospheric warming and drying is exponential. Anything that goes exponential, if you see an exponential plot, there's reason to look at that thing and really think and make sure you understand it. We know after a pandemic how crazy exponential processes can get in a very short amount of time. Well, this is what climate models say is going to happen in the future because of the vapor pressure deficit. The black record is our observed record of the vapor pressure deficit. Again, this is the sponginess variable dictated by heat and humidity. And if we keep burning fossil fuels basically as fast as we can, then we're looking by the middle of the 2000s, by 2050 or so, we're looking at a case where the average year is as warm as dry as the extreme recent years like 2020 and 2021 that drove these huge record-breaking fire sizes. If we start slowing our burning of fossil fuels, then we will take a different trajectory. We still have warming in store, but these two worlds become very, very different by the 2050s, and so this is something to think about. But predicting how future fires can respond to climate is really, really complicated. That's illustrated by this picture here. If you dry out this forest, then you'll get a big fire. But after you have this big fire and you've thinned out the forest or removed big chunks of forest, then presumably the next big drought isn't going to be able to cause a fire that can blow through this area nearly as quickly. So the ecosystems of the West are very complicated, and the future of fire in the West is also going to be very complicated. If we want to understand how fire is going to continue changing in the future, not only do we need to be able to model or estimate how climate's going to change, but we need to model or estimate how forest ecosystems are going to change, not only in response to climate, but actually in response to fire. Fire affects forests, and forests affect fire. And so I've been working, and I'm wrapping up here, I've been working hard over the last year to develop a new fire model for the Western United States forest region. And this is the very first time I've ever shown this model to somebody who's not a close collaborator of mine. I just made these plots 2 days ago, actually. And it's hard to tell the story of this, but what we're doing is simulating monthly fire probabilities and monthly fire sizes across the West. And this is a very complicated model where not only are the fires responding to climate, but they're also actually responding to changes in forest ecosystems. The fires are affecting forest ecosystems in this model. This model is keeping track of how many seeds are in the soil and what the species are of the seeds and what type of seed is going to turn into a tree under different climate conditions. So different species are competing with each other. When there's a fire, the forest gets thinned, and then that reduces the probability of a future fire for a while. The fires are also responding to changes in human population in this model. And so I could give a whole hour on this model and how it needs more work, but it's also pretty cool. But I'll skip to something that's promising, and that is if we take all those monthly simulations, and with the model that I was just showing you, we actually run the model 500 times, and each time things play out a little differently because there's a lot of randomness involved with fire. But if you average together all the 500 simulations, you get the black line. This is a record of the number of forest fires in a given year. And you can see that the black line looks pretty darn similar to the observations, the red line. And here we can compare the amount of forest area that burns in a given year that we predict with our model. Again, the black line, compare that to the red line. Now, the black line should never look just like the red line because there's a lot of randomness involved with fire. But the red line should look something like the scatter of gray lines, the 500 different simulations. And so what I'll say now is we're not doing this perfectly. There are improvements to make, but we now are on the precipice of having a really great model that we can use to simulate how fire is going to change in response to climate, as well as things like land management. We can run simulations where we say, what if we start doing prescribed burns and thinning forests in certain areas? Can we reduce the fire risk in Big Bear, for example? Fire also affects the amount of water that we have. Oftentimes you hear that climate change is going to lead to less water availability for humans. I made that case earlier. But if you remove a huge amount of forests from the Western United States mountains, that means less trees are using water when it falls on the landscape. And we can actually use these amazing stream gauge records that the USGS has been maintaining for over 60 years now to see that after fires, stream flow out of forested areas increases by, on average, 20 to 30% for at least the next 6 years after the forest fire. Here I'm showing you in the average stream flow across 29 different forested watersheds in the Western United States that all burned severely sometime in the last 30 years or so. The blue record is what I estimate should have happened to stream flow based on climate. The fact that we have a drying climate should cause stream flow to decrease. The red record is what actually happened. In river basins where there was no fire, our predictions of stream flow sit perfectly on observations. But in stream watersheds that burned, we see consistently that we've been getting more river flow than we would have without the fire. This could be a silver lining, where an increase in fire may actually lead to enhanced water availability for people in parts of the western US by reducing the rate of climate change-induced drying. But water is only a good thing if you expect it. Water is heavy, it's destructive, and when it shows up unexpected, say if you have a big storm over where the Dixie Fire occurred in the northern Sierra Nevada and you have way more water running off of the mountain than you expected, if water managers aren't expecting larger than normal pulses of water coming out of the mountains, then what could be a silver lining good thing could very quickly be a disaster. It was only 5 years ago now that Lake Oroville almost overtopped because of a surprisingly high amount of runoff in the northern Sierra Nevada. And so I'll conclude by just saying that, once again, because of Keeling's work and the geniuses that preceded him, we now know that humans are embarking on a crazy experiment with atmospheric chemistry, and we know that atmospheric chemistry causes changes in climate. We now need our best and brightest kids to be motivated to become scientists or to become economic experts or political experts, because we need to understand not only the climate system to be able to model how climate changes as a result of CO2, but we need to understand how we are going to respond to this. Economics and politics are going to drive whether or not CO2 continues to skyrocket like this or curve back down. And most of us care a lot about where we live locally. And it's not necessarily in any of our hands whether or not CO2 continues skyrocketing or starts leveling out, but we can do something about how it feels locally. And so we need people to do the stuff that I'm interested in, which is try and model or be able to predict how our landscapes are going to change as a result of climate changes that we may not have such a big choice about. And finally, I'll finish with a quote from Charles Keeling from kind of a memoir paper that he wrote in 1998, where he describes his motivation early on for developing these initial precise measurements of CO2, where he says, "It was a full day's drive to Big Sur. Not being sure that the CO2, even in pristine air next to the Pacific Ocean, would be constant, I decided to take air samples every few hours over a full day and night, as well as a series of water samples. Why did I devise such an elaborate sampling strategy when my experiment didn't really require it? The reason was simply I was having fun." When we're doing what we're most interested in, that's when we make our biggest discoveries. This is something that I think everybody should have in their mind when they hear about a scientist going through their career, because scientists like Charles Keeling have a harder and harder time getting to continue doing what they love because of many, many other expectations. And so if you meet a scientist, ask the scientist what they love and see if you can encourage them to actually spend the next few hours thinking about that rather than politics or administration or some of the other things. And with that, thanks very much. Thank you.
Yeah, so thanks so much. You made me think, yes, this is fun tonight. Having fun, so that's great. So there's certainly time for a few questions, so I hope we can take them. Okay, good.
Yeah. How do you measure vapor pressure deficits in the distant past, and how far back can you go with measuring vapor pressure deficits, and how do you measure the old ones?
That's a great question. So how do we know what vapor pressure deficit was like back in time? Well, we can measure it precisely. It's just actually the product of temperature. Temperature caused vapor pressure deficit to go up, and humidity. The more humid the atmosphere, then the lower the vapor pressure deficit. But vapor pressure deficit is really driven by temperature. In the western United States, or across most of the United States, we've got pretty darn good records of temperature going back to the 1920s, and in some areas going all the way back to the late 1800s. And so we've got a pretty good idea of what the vapor pressure deficit was doing over the last 122 years, but uncertainty kind of grows as you go further back in time in that period. Before that, though, we don't know exactly what vapor pressure deficit was doing. We have tree ring records, but tree ring records aren't specifically vapor pressure deficit records. Tree ring records are records of tree growth. And tree growth is dictated not just by the dryness of the atmosphere, the vapor pressure deficit, but how much water is in the soil. The amount of water that's in the soil is dictated by precipitation, but then also the vapor pressure deficit. And so I haven't been bold enough to try and use tree ring records or anything else to actually reconstruct vapor pressure deficit specifically back in time. The reconstructions I was showing earlier are just soil moisture.
Thanks, great talk. Just a question, you showed the exponential growth and burn area over time in the observations, and I was just wondering if your new fire model predicts that trend will continue into, say, the next 100 years?
That, I think it does, but the fire model, so this fire model is so hot off the press that I actually have not run any simulations into the future. Running simulations into the future is more complicated than running simulations for the past because you need to create climate data sets that represent the future. And of course we have the climate model data that I was showing you before, but those are a much lower resolution. There's a lot of work to be done to prepare those data sets to actually be used to make future simulations of fire. But what we see, but the model does simulate the exponential response of forest fire area to drying as we've seen it in the past.
Thank you for the inspiring talk. I was wondering, you showed the tree ring record, and maybe it was just by chance, but the period just before this recent drought also happens to be the wettest in the entire record. And I was wondering if you could comment on that a little bit.
Yeah, so the 1,200-year record I showed you with soil moisture, if you look at the 1980s and 90s, it's true that was actually, according to this reconstruction, the wettest 20-year period in the last 1,200 years. Now, there were some exceptionally wet years. There were some really big El Nino events that delivered huge amounts of water to the west during that time. But I'm actually kind of skeptical of that conclusion that the 80s and 90s were actually the wettest 20 years. Trees are these living things that kind of experience the law of diminishing returns when it comes to water. When things are really dry and they get a little bit of water, then the growth response is really good, or is really noticeable. Once conditions are already wet and a little more water isn't going to make that big of a deal. And so our reconstructions of drought, I think, are a lot more precise, actually, than the reconstructions of wetness. So I should revisit this work and actually work on making the error bars represent that. I think our uncertainty on the wet side of the reconstruction is a lot wider, actually, than the reconstruction on the dry side of the reconstruction.
Hi. I'm still trying to get a grip on what you were saying about the streamflow changes. And can you speak a little more about streamflow change and how it might relate to habitat type conversions over time, and kind of in the context of like urban heat island or the vegetation sort of creating its own climate, and if it's gone, even though the water's coming, will it keep coming over time if the forest is gone, especially in a foggy region?
Yeah, thanks. Yeah, geez, there's a lot there and a lot of interesting parts to the question. I'll see what I can hit in about a minute. And the streamflow study, I just showed one figure. I was really excited to talk about that work because it's new and exciting. But yeah, I didn't give it enough attention to really make it all that understandable. But we looked at streamflow gauges across the West, and we were able to compare stream gauge records in areas that had experienced forest fire recently versus areas that hadn't. And what we saw is that after forest fires, there's a divergence between the amount of water that actually was flowing in the streams and the amount of water you'd predict based on climate. If you go outside of the forest fire areas, there wasn't that divergence. Streamflow remained as predictable in the 2000s as it was in the 1900s. More streamflow is occurring after fires. How is this affecting habitats? Well, like riparian habitats, I can't speak to it. I know hardly anything about riparian habitats, like river habitats, unfortunately. I know that after fire, water quality tends to decrease. There's huge amounts of erosion, pollution goes up, and so temporarily habitats may not experience much of a benefit from an extra pulse of water for a few years after fire. Urban areas, though, although enhanced pollution and erosion following fire may make water management hard. Our dams, for example, weren't really set up to be able to handle gigantic unexpected influxes of sediment that occur after erosion. You're asking about the urban heat island, and that's something that's really interesting, where in Southern California, cities have definitely been warming up. And if you go to the center of a city, it's been warming up further or more than on the outskirts. The temperature of the ground in coastal Southern California actually, this is something I didn't get to talk about in the talk, but I'll just say now, the temperature of the ground actually affects our June gloom, May gray, August fog clouds. The colder and wetter the ground, the lower the clouds are and the harder they are to burn off. Because of urbanization in LA, warming surfaces are actually causing the clouds to develop higher in the sky. But the clouds are squeezed into a marine layer, and so the clouds just can't keep going up forever. Instead, the clouds are getting thinner and thinner. That means coastal areas are actually getting more sunlight today than they would otherwise, because there's less cloud shading. This actually feeds back to change fire risk in coastal areas, probably something I worked on a few years ago, but definitely needs a lot more work on. People concerned with energy consumption or inequities when it comes to access to air conditioning should be looking at this in the LA area, where places that never would have needed air conditioning 40 years ago not only are experiencing increased risk of dangerous heat because of global warming, but even more so because of local warming and degradation of the marine layer.
Okay. So my question kind of extends on the stream stuff. So if there's more water in the streams post-fire, and presumably it's flowing through the area faster, would that change the amount of groundwater that you are potentially rebuilding? I know they're very different timescales, but I was just wondering about that.
I think probably in the area where probably more water in the stream area means higher water tables, or in the area where the stream is. If we're getting more water, like there are some areas, and I'm not an expert in this at all, but there are some areas where people are doing a pretty good job at recharging groundwater in areas where we had historically over-extracted. And so in that case, there may be more reservoir water to be able to direct toward groundwater recharging because of the enhanced runoff efficiency after fires. So these are important things to be thinking about. Like, can we benefit actually from the enhanced stream flow after fire? But of course, I think the only way we can is if we expect the increase in stream flow after fire, so we don't get surprised. Otherwise, that water doesn't end up being usable. We are letting it out of the dams in a real panic in order to avoid flooding.
So thank you. I'm curious about the size of the area that you evaluated, and especially now with all of the U.S. Forest Service and Gavin Newsom's desires to address forest density, if you have enough granularity that you could see the changes that are coming with all the upcoming fire management work.
Yeah, we should be able to. If there are changes, we should be able to see them. The spatial scale of what we're looking at here is the entire Western U.S., and I was simplifying things by taking the entire Western U.S. and showing you an average record that represents the whole thing. But of course, every individual place has its own story and doesn't necessarily look like the regional average. But in our studies, we're looking at this granular level too. Now, not necessarily at the scale of a city block, but say a few miles by a few miles. The simulations that I was showing you work on the 1 kilometer scale, so about 0.6 mile by 0.6 mile. And so we should be able to, if there is a giant treatment where forest densities are reduced across a very large area, we should be able to simulate what the effect of that should be. And after several years, we should be able to actually start seeing, did those treatments actually have an effect? For example, if a fire gets going over in this untreated area and starts burning into this place where we've done prescribed burning or aggressive forest thinning, was there actually a detectable effect? And in any individual place, the story is going to be really hard to decipher. But if we're doing these treatments across enough places, then the data should bear out whether or not there's an effect or not.
Okay, well, thank you so much.
Yeah, thank you all. This is really
yeah,
nice.
Yeah, it's a really, really stimulating evening. There's so much to take home and think about here, so it was really, really fascinating. And I want to also thank the aquarium staff for the great job in setting this up. And again, what a wonderful presentation. So thank you.
Thank you, Ralph. Thanks, everyone.
And you may have noticed there is food. I think it is actually for you guys.